Just an overview of the carbohydrate. That carbohydrates are the polyhydroxyaldehydes and ketone. It can classify it into the mono, di, oligo and polysaccharide, held together by the glycosidic bonds and supply the energy and serve as the structural constituent. So it is the polyhydroxy. Why it is called as the polyhydroxy aldehyde or ketone? Because this aldehyde group and the keto group is present and multiple hydroxyl group is present in the carbohydrate. So all this part we already described in the last lecture. So classification of the monosaccharide based on the number of carbon, that here it is the CH2OON. So in the case of monosaccharide, the N can be vary from 3 to 7. So if the number of N is 3, then we can call this as a triose. Like that, if N equal to 4, then tetrose, 5 pentose, 6 hexose and 7 heptose. So in each category there is two different classification. One is for the aldose and another one is the for ketose. So if aldehyde group is present, then it is known as the aldose, and if keto group is present, then we can classify it as a ketose. So represent of the carbohydrate structure. There are different types of representation for the carbohydrate. There is mainly three types. One is the Fischer projection, another one is the chair conformation and the Haworth projection. So let's discuss each and every representation structures. First one is the Fischer projection. It is developed by the Hermann Emil Fischer. It is mainly used to represent the open chain structure of the monosaccharides. It can represent the 2D structure of the 3D molecules. The carbon chain is drawn vertically with the most oxidized group, aldehyde or ketone, at the top, and horizontal lines represent the bonds coming out of the plane. That means it is towards the viewer, and the vertical line represent the bonds going beyond the plane. That means away from the viewer. So we can classify it like this, that it is a vertically we can draw a line. It is the carbon chain with the most oxidized group, aldehyde or ketone, at the top. So either CHO at the top or and CH2OH at the bottom. And there is the horizontal line. Several horizontal lines. These horizontal lines actually represent the bonds that coming out of the plane, that means towards the viewer, and this vertical line actually represent that the bonds going beyond the plane, that means away from the viewer. On the base of the OH group at the penultimate carbon, we can classify this into the two configuration. One is known as the D configuration and another one is the L configuration. So if the these OH, it is the penultimate carbon. Why? Because the most oxidized group CHO or the keto at the top. So from the top, which is the farthest carbon, so we have to consider this carbon. In this carbon, if OH in the right hand side, then we can classify this as a D isomer, and if the OH is in the left hand side, we can classify this as a L isomer. So if at the oxidized group the aldehyde is present, then both can be considered as a aldose, and if the keto group is present, then we can consider it as a ketose. But for the ketose also, from the keto group, the farthest carbon we have to consider, and in this carbon, if hydroxyl group in the right hand side, then we can call it as the D isomer, and if it is in the left hand side, then we can call this as a L isomer. So first we will describe about the structure of the monosaccharide for the hexose family, aldohexose family. So hexose means the 6 carbon molecules are there. In this structure, the 4 chiral center we can get. So 4 chiral center means the number of stereoisomer equal to 2 to the power of n. That means 2 to the power of 4 in this case. So in the case of aldohexose family, we will get the 16 stereoisomer. First one, that for this aldohexose family structure, we have to remember one line. From the line, we can easily get all the structure name. The line is all altruists gladly make gum in gallon pan. From this all, we will get the first aldohexose member, which is known as the allose. So what is the structure of the allose? This one. That first CHO at the top, it is the oxidized group, and CH2OH at the bottom. And we can see there is the 4 chiral center, 1, 2, 3 and 4. For the allose, all the hydrogen in the left hand side. So for the C, it is the C1, so it is the C2. So for the C2, first hydrogen is the left hand side and OH in the right hand side. Similarly, for the C3, H in the left hand side, OH in the right hand side. For C4, H in the left hand side and OH in the right hand side. And the penultimate carbon, so it is the D-allose structure. So for this case, the OH in the right hand side. This is the structure of the D-allose. Next, from the altruist, we will get the second member of the aldohexose family. The name is altruist. So for this, from this altruist, the name is the aldose. So for this aldose structure, the CHO again at the top and CH2OH at the bottom. Then again we have to decide that first carbon HO is the left hand side and H in the right hand side. Rest of the carbon same structure with the allose, that H in the left hand side for the C3, C4 and C5, and for all the case the OH in the right hand side. So this is the structure for the D-aldose. And so in this case only the change in the configuration for the number of carbon C2. Then from the gladly we will get the third member of the aldohexose family. The name is glucose. So for the glucose structure, again the same, that CHO, the most oxidized group at the top and CH2OH at the bottom. Then respectively for C2, C3 and C4, the structure is that H for the C2 is left hand side and OH in the right hand side. But in the case of C3, the change is the HO in the left hand side and H is on the right hand side. Same for the C4 and C5 like the aldose and the allose family. So it is also the D-glucose. This is the D isomer again. So for the D isomer for all the aldohexose family, the last carbon, that means C5 penultimate carbon, OH in the right hand side and H in the left hand side. Then from the make we will get the next structure, that is the mannose. So for the mannose we will get that the change in the position for the 2 carbon. One is C2 and another one is the C3. So for the C2 and the C3, HO in the left hand side and H in the right hand side. But in the case of C4 and the C5, similar with the another structure like glucose, aldose and allose. For all the case, H in the left hand side and OH in the right hand side. Next is from the gum, we will get the name of the next molecule, that is the glucose. So for the glucose structure again, the CHO at the top and CH2OH at the bottom. And here the only changing position is C4. C2 and C3 is similar with the D-allose and only case of the C4, the HO in the left hand side and H in the right hand side. And in the case of C5, it is the structure of D-glucose. So H in the left and OH in the right. Next, for the we will get the next structure, that is the iodose. So for the case of the iodose, there is the changing position for the two C2 and C4. So C2 and C4, HO in the left and H in the right. Then C3 and C5, H in the left and OH in the right direction. After that, from gallon, we will get the next structure, that is the galactose. And for the galactose, there is the changing position for the C3 and C4. So for the C3 and C4, HO in the left side and H in the right hand side. It is the structure of D-galactose. So ultimately, the C5 carbon, the penultimate carbon, OH in the left and OH in the right and H is the left direction. And ultimately from the tank we will get the last member, the name is the telos. And in the case of telos also, the changing position is the C2, C3 and C4. For all this case, HO, the hydroxyl group, in the left hand and all the H in the right hand. Only the penultimate carbon which will decide that it is the D configuration or L configuration. So in this penultimate carbon only, because of this D isomer, that OH in the right hand and H in the left hand. So if we actually consider the D-allose as a reference, then we can say that with respect to allose, only the changing position C2 for the aldose. Then for the glucose, the changing position is only the C3. With respect to allose, for the case of mannose, the changing position is C2 and C3. Then for the gulose, the changing position is only C4. With respect to D-allose, the changing position for iodose is the C2 and the C4. And in the case of the galactose, the changing position is C3 and C4. And for the case of D-allose, the changing position is C2, C3 and C4. So the overview is that if we remember the line, all altruists gladly make gum in gallon tank, we can understand the total 8 structure of the aldohexose family. All these 8 structure, the D configuration. If we change the position of the C5 configuration, that means if for the C5 that HO and H will be reversed, then we will get the L configuration. And with respect to, if we consider the allose as a reference, then C2 for the aldose, C3 for the glucose, C2 and C3 for the mannose. For gulose, it is C4. For iodose, it is C2C4. For galactose, C3C4. And for telos, C2, C3 and C4 will be changed. Then all the D isomer, if we just make a mirror image for all the structure, we will get the L isomer. So for the 8 D isomer, we will get 8 different L isomer. So the total number of stereoisomer is 16. So if we consider the D allose, so all the H is in the left hand and all the OH in the right hand. So just the mirror image of the D-allose, we will get the L-allose. And in the case of L-allose, all the hydroxyl group in the left hand and all the hydrogen in the right hand. Similarly, in the case of the aldose, glucose, mannose, glucose, iodose, galactose and talose, if we take the D isomer and we make a mirror image of this D isomer, we will get the L isomer for all the structure, and all are the enantiomer in nature. But we should remember one important thing, that if a molecule is dextrorotatory, that means plus, then its enantiomer will be levorotatory. Or if the molecule is levorotatory, the enantiomer will be dextrorotatory. But it does not mean that D isomer means the plus or dextrorotatory, or L isomer means it is minus or the levorotatory. The D-allose is actually plus, dextrorotatory in nature. So its enantiomer L-allose must be minus. That means levorotatory in nature. In the case of iodose, it is the D-iodose is minus, that is the levorotatory in structure. The L-iodose should be plus, that means dextrorotatory in nature. D means not dextrorotatory. L means, capital L means it is not levorotatory. Then we will the structure of the aldopentose family. For the aldopentose family, the number of chiral center is 3. So ultimately we will get total 2 to the power 3 is equal to 8 stereoisomer. If we remember the structure of the aldohexose family, we will easily get the aldopentose family member structure. How? If we consider the first two member of the aldohexose, that is the D-allose and D-aldose, we can get that all the position is same except the C2. Similarly, if we consider the D-glucose and D-mannose, except the C2, all other structures are same. All the other carbon configuration is same. If we consider the glucose and iodose, similarly, except C2, all other position is same. If we consider the galactose and talose, except C2, all the positions are same. So when we will come to the aldopentose family, if we just delete the C2 from the first two member of the aldohexose, we will get the first member of the aldopentose family. This is the D-ribose. So if we see that in the case of D-ribose, only the C2 carbon is omitted. Rather than this, that C1 is CHO, here is also the last carbon is CH2OH, here is CH2OH, and except C2, that C3, C4, C5, all the position hydrogen is the left hand side and OH in the right hand side. Similarly, from the next two pair, that is the glucose and mannose, we will get the next member of the aldopentose family, that is D-arabinose. So if we delete the C2, we will get the rest of the position and we will get the D-arabinose. So CHO at the top, CH2OH at the bottom, C3 for the case of glucose and mannose, here is HO in the left, H in the right. In the case of arabinose also, that HO and H, then HOH for the C4, and also in the case of C5 it is the D, so H in the left and OH in the right. From the next two pair, that is the glucose and iodose, we will get the next member, that is the xylose. So if we again delete the C2, we will get the xylose of the third family member of the aldopentose. And again from the last pair, that is the galactose and talose, we will get the last member of the aldopentose, that is the lysose. So in the case of lysose, that C2, C3, that HO in the left, H in the right, and it is D isomer. So ultimately for the penultimate carbon, that is the C4, H in the left and OH in the right. For the enantiomer, just we have to draw the mirror image of all the structure. Then we will get the L isomer of the D isomer. So there is the 4 D isomer for the aldopentose family. So there should be another 4 L isomer for this aldopentose family. So total 8 stereoisomer we will get. If we see the D-ribose, for the mirror image, we will get the L-ribose. For the D-ribose, all the H in the left and all the OH in the right. Similarly, case of the L-ribose, all the OH in the left and all the H in the right. Similarly, we will get the structure of the L-arabinose, L-xylose and L-lysose. Next, we are coming to the aldotetrose and the aldotriose family. So, if we know about the aldopentose family, so from the aldopentose family, we can easily get the member of the aldotetrose and aldotriose. So, these D-ribose, arabinose, xylose and lysose are the member of the aldopentose family. So if we consider the first two pair, the ribose and arabinose, we can get that only the changing configuration carbon number is C2. Other than C2, the C3, C4, all the configuration of the carbon is same. So if we delete the C2 carbon, then we can get the structure of the first member of aldotetrose family. This is the erythrose. Similarly, if we consider the next pair, that is the xylose and lysose, and again we can see only in the C2 carbon the configuration is different. Other than C2, the C3 and C4 are same. So if we delete the C2 carbon, we can easily get the next member of the aldotetrose family, that is the triose. And from the D-erythrose and D-triose, we can easily recognize that again the C2 carbon, the configuration is different. So if we remove the C2 carbon from this erythrose and triose, we will get the next molecule and one the aldotriose molecule, that is the glyceraldehyde, and it is the D-glyceraldehyde. That's why hydrogen is the left hand side and OH in the right hand side. If we do the mirror image of the erythrose and triose, so from the D configuration, we will get the L isomer, and this D erythrose and D L erythrose are the enantiomer. Similarly, from D triose, we will get the L triose, and from D glyceraldehyde, we can easily get the L glyceraldehyde structure. Next, it is the ketose family. Ketose means the keto group is there as an oxidizing group, and it is under the ketose family. Again, we can get the hexose family, and in the case of ketohexose, the number of chiral center is 3. So ultimately, we will get the total 8 isomers for the ketohexose family. First one is the Sucrose, then fructose, sucrose and tagatose. Similarly, in the case of Sucrose, C1 is the CH2OH and C6 is the CH2OH, and C2 is the oxidized group, that is the keto group, and then C3, C4 and C5, all the position, the hydrogen is the left hand side and OH in the right hand side. In the penultimate carbon, that means the farthest carbon from the keto group, the C5, OH in the right direction, that's why it is the D isomer of the Sucrose. If we take as a reference of the Sucrose, we can again get the fructose, sucrose and tagatose. With respect to Sucrose, for the D-fructose, only the changing position is C3. Other than C3, all the other configuration, all the other carbon orientations are same only. With respect to Sucrose, only the changing position is C4 for the sorbose, and C3 and C4 both position are changed for the tagatose. All are D isomer, that's why in all the cases C5 carbon hydroxyl group in the right hand side. Then if we do the mirror image of these four molecules, we will get the L isomer of these four molecules. Similarly, that is the L Sucrose, L fructose, L sorbose and L tagatose. So total 8 isomers, 8 stereoisomers we are getting from this ketohexose family because they have the 3 chiral center, 1, 2 and 3 chiral centers. So 2 to the power 3 equal to 8 stereoisomers. Similarly, we will get from the ketohexose, that is the ketopentose family. And in the case of ketopentose, there is a 2 chiral center. So for this 2 chiral center, there is total 4 stereoisomers. Again, we consider the first two pairs of the ketohexose, that is the Sucrose and fructose. We will get that is only the C3 position is different. So if we delete the C3, then we will get the first molecule of the ketopentose, that is the xylulose. And again, if we consider the next pair, that is the sorbose and tagatose, again the C3 molecule is different. So if we delete the C3 molecule, we will get the next molecule of the ketopentose, that is the ribulose. In the case of xylulose and ribulose, both the case they are D-isomer. That's why in the penultimate carbon, that is the C4, the hydroxyl group is the right hand side and hydrogen in the left hand side. If we consider the enantiomer, that means mirror image of the xylulose, we will get the L-xylulose. And if we take the mirror image of D-ribulose, we will get the L-ribulose. So total 4 stereoisomers we are getting under the ketopentose family. From the ketopentose family, we will get the ketotetrose. From the xylose and ribulose, again we can see only the C3 position is different in their orientation. So if we delete the C3, we will get the ketotetrose molecule, that is the erythrulose. So it is the D-erythrulose, that's why OH in the right hand side and H in the left hand side. If we take the mirror image of the erythrulose, we will get the L-erythrulose. And from the L-erythrulose, we will get, that is the D-hydroxyacetone. We can say it is normally hydroxyacetone because it is achiral, so does not exhibit the optical activity. Therefore, they don't have no specific orientation, that is the dextrorotatory or levorotatory, because it is achiral. Up to this, it is the Fischer projection of the monosaccharide. Next, we will discuss about the Haworth projection of the monosaccharide. First, what is the Haworth projection? Haworth projection is a 2D diagram that represents the 3D cyclic forms of the sugar. Either it is hemiacetal or it is the hemiketal. It is particularly useful for visualizing the alpha and beta anomer and the ring size, that is the pyranose for the 6-member and furanose for the 5-member ring, and the relative position of the hydroxyl group. How we can get the Haworth projection? Monosaccharide with 5 or more carbon can cyclize through an intermolecular reaction. If it exists as an aldose, then then it will form the hemiacetal. How? The aldehyde group of the C1 and the OH group of the C5 will interact with each other. And similarly, a ketose if there under the monosaccharide, then the hemiketal will form. The keto group of the C2 and the OH group of the C5 will do intermolecular reaction to form a hemiketal ring. The C5 hydroxyl actually attacks the C1 carbonyl in aldose to form a six-membered ring known as the pyranose. And the C5 hydroxyl attacks the C2 of the carbonyl in ketose to form a five-membered ring known as the furanose. This is the general structure of the pyrene and the furan. So from this general structure only, we will get the pyranose and furanose structure. Next, that is the features of the Haworth projection. At first, it will form a ring structure. It is a planar ring with the ring oxygen at the upper right. The ring is not actually flat. It is a simplification rule. How the position of the substituent? That groups below the ring came from the right in the Fischer projection. So it is the Fischer projection of the D-glucose. So in this case, water in the right hand side, that is that for the C2, that is the OH, for C3H, all the right hand side molecule will come in the below position. And all the left hand side molecule will go above the ring. The new stereocenter form two anomer, either the alpha anomeric form or the beta anomeric form. The anomeric carbon is the C1. If the OH on the anomeric carbon is down, then we can consider it as a alpha anomer. And if OH in the anomeric carbon is up, then we can say it is the beta isomer. Like it is the general Fischer structure of the D-glucose. So the glucose is the aldohexose family. So in the case of aldose, the C5OH molecule react with the C1 molecule, that means the aldehyde group, and form an intermolecular interaction, and this hemiacetal will form, then the pyranose structure will form. And all the right hand side molecule at the down position and all the left hand side molecule at the up position for the Haworth. And in this case at the C1, the hydrogen is the upside and OH in the downside. So this structure is actually the alpha anomeric structure. Like that actually the mechanism is happening. The C5 OH is actually react with the C1 group of the aldehyde, and then here one intermolecular interaction, one bond will form, and then this pyranose structure will form. This is the general structure of the glucopyranose, D-glucopyranose. So according to the position of the H and OH group, that up or down, it will depend that it will be the alpha anomer or the beta anomer. From the D-glucose, similarly like that only we will get, that is the alpha D-glucopyranose structure and beta D-glucopyranose structure. For this alpha, H upside, and for the beta, H is the down. And if it is the L-glucose, similarly we will get the alpha L-glucopyranose structure and beta L-glucopyranose structure. From the fructose, we can generate the furanose structure. So it is the D-fructose family. From the D-fructose, again we will get the alpha D-fructofuranose if the OH in the downward, and if OH in the upward, we will get the beta D-fructofuranose. For the case of the fructofuranose, actually, it will form the hemiketal. The C5 group, the hydroxyl, will attack with the C2 of the carbonyl, and then this furanose structure will form. Similarly, in the case of ribose, that is the aldopentose, again the furanose structure will happen. The C4 hydroxyl group will attack with the C1 aldehyde group, and then this furanose molecule will appear. If OH in the downward, then it is the alpha D ribofuranose, and if OH in the upward, it is the beta D ribofuranose. Similarly, other aldopentose structure and other ketohexose structure we can generate like this only. After this, the Haworth projection. Next, we will start that the chair conformation structure. So why the chair conformation? All the Haworth conformation and the Fischer conformation both are actually for the 2D structure, but the chair conformation actually represent the 3D structure. When the monosaccharides such as glucose form the cyclic structure, they usually adopt the 6-member rings known as the pyranose. Although these rings are often drawn as a flat hexagon, that is the 2D, but in reality they are not in planar. It is actually represent the 3D structure, and this 3D structure actually we can generate in the chair conformation. The shape is like a chair, that's why it is known as a chair conformation. What is about the structure? This is actually the chair conformation structure. In the chair conformation, the 4 carbon atoms lie in one plane. While one carbon tilts upward, another carbon tilts downward. Each carbon in the ring has 2 substituents. One in the axial position, that is pointing up or down parallel to the vertical axis, and one in the equatorial position, projecting outward, roughly horizontal or diagonal to the ring. From the D-glucose, again in the chair conformation also, we can get alpha D-glucopyranose and beta D-glucopyranose. How? That again this C5 hydroxyl group will attack the aldehyde group of the C1, and then this interaction will happen. And after this mechanism, this molecule will form, that is the alpha D glucopyranose and beta D glucopyranose. We can say that in the case of C1, if hydrogen is in the equatorial position, for the case of C2, which is in the left hand side, it will be in the axial position. Means for one carbon, if the left hand side molecule, for one carbon, left hand side molecule like here the C1 hydrogen, if it is in the equatorial, next carbon left hand side molecule will be in the axial. Again the next carbon left hand side molecule will be in the equatorial. Again then for next one it should be in the axial. That means in alternative way. For the case of alpha and beta, if OH in the axial position, then we can get the alpha anomer. If OH in the equatorial position, we will get it is as a beta position. Other than this C1, all other configuration will be same for alpha and beta. The most stable conformation occur when all bulky group, especially the hydroxyl group, are in the equatorial position. That's why the beta D glucopyranose is the most stable structure, because we can see that C1, C2, C3, C4, C5, all the position, the hydroxyl in the case of beta D glucopyranose in the equatorial position. But in the case of alpha D, the C1 OH in the axial. That's why in between C1 and C2, there is a axial OH interaction, and that's why alpha D glucopyranose structure is not too much stable. The beta D glucose is the most abundant sugar in nature and energetically favored also for its stability. Other than this, it has one conformational isomerism also, which is known as the flip. The ring can undergo a process which is called the chair flip. That means where axial groups become equatorial and vice versa. There is no other change like D or L or alpha or beta. Just all the axial group in the equatorial and all the equatorial will be in the axial. After a flip, the molecule exists in a different conformation, which may be more or less stable depending on the position of the substituent. For glucose, the flipped form is less stable as several OH group in the axial position that cause the steric hindrance. That's why that without flip structure for the glucose is the most stable one. So for this chair flip, confusion is happening. First one, the doubt. After flipping, the beta D-glucopyranose will convert to alpha D-glucopyranose? The answer is absolutely not. Because the flipping of the chair conformation, beta D-glucopyranose will not convert to alpha D-glucopyranose. Because beta and alpha, these are the anomeric form. If there is only the change in the C1 position hydroxyl and H group, then we can consider it as an anomer. But in the case of chair flipping, all the axial group will be in the equatorial and all the equatorial act as an axial. So there is no anomeric conformation change. Next doubt is that after flipping beta D glucopyranose will convert to beta L glucopyranose? For these also answer is absolutely not, because in the flipping there is no conformational change like D and L. D and L, that means it is the enantiomeric changing, but here there is no enantiomeric changing. It is just a flip, that axial in the equatorial in the axial. But D and L means that is completely the mirror image relationship, the enantiomeric relationship. Similarly, like glucose, the other molecule of this allose, aldose, aldohexose family, we can also generate the chair conformation, and only the C1 position will be changed for the alpha and the beta anomeric carbon. Next, the disaccharide, the next level of the carbohydrate. The disaccharide means the two monosaccharide will join, by which they will condense to each other. So dehydration reaction will form, and after the reaction the glycosidic bond will form and the water molecule will release. There is the empirical formula of the disaccharide, that is the C12H22O11. Taste is sweet. Some disaccharides are less sweet. It is generally highly soluble in water due to the presence of the multiple hydroxyl group in the structure. The disaccharide means two monosaccharides are linked by the glycosidic linkage, may exist as a cyclic form in solution. Then the formation of the glycosidic bond. How this glycosidic bond actually formed? Two monosaccharides joined together by dehydration reaction. A water molecule is released as a bond forms between the anomeric carbon of the one sugar, with hydroxyl group of the another carbon. The linkage is referred to the glycosidic bond. Its position and stereochemistry determine the properties of the disaccharide. In this maltose molecule, two glucose unit will join. Both the glucose is the alpha D glucose. One alpha glucose anomeric carbon hydroxyl group is linked with the another alpha glucose, that C4 hydroxyl group, and here the condensation reaction will form, the dehydration will occur, water molecule will remove, and this glycosidic bond is formed. In this case, that alpha glucose at one anomeric carbon will react with the another alpha glucose C4 hydroxyl group. The glycosides are formed when the hemiketal or hemiacetal hydroxyl group of a carbon reacts with the hydroxyl group of another carbohydrate or non-carbohydrate also. If it is react with a carbohydrate, then it is known as glycoside. If the bond is non-carbohydrate, then it is known as the glycon. The monosaccharides are held together by glycosidic bonds in the disaccharide, oligosaccharide and polysaccharide. How the name of the glycosidic bonds occur? The nomenclature of the glycosidic bond is based on the linkage between the carbon atom and the status of the anomeric carbon. In the maltose, the bond between the C1 of alpha glucose and C4 of the alpha glucose. So that's why the glycosidic bond name is alpha 1,4 glycosidic bond. Both are alpha glucose and C1 is bond with the C4. That's why alpha 1 to 4 glycosidic bond in maltose. Disaccharide consists of two monosaccharides unit held together by a glycosidic bond. So these disaccharides are two types, that is the reducing and non-reducing. The reducing means if free aldehyde or keto group is present, that means it have a free anomeric carbon that can undergo the oxidation, then it can known as a reducing disaccharide. Like in the case of maltose, that one alpha glucose anomeric carbon is linked with the another alpha glucose C4 hydroxyl group. So for the another alpha glucose, the anomeric carbon is free. So another alpha glucose, what C4 is linked, this alpha glucose actually reducing, and for one alpha glucose whose C1 is linked, it is the non-reducing. Combinedly, the maltose is a reducing disaccharide. What are the non-reducing disaccharide? That the non-reducing disaccharide with no free aldehyde or keto group. That is, they have no free anomeric carbon because both are involved to form the glycosidic bond. Like in the case of the sucrose. In the case of sucrose, the alpha glucose is linked with the beta fructose. In the case of the sucrose, the alpha D glucose C1 is linked with the beta D fructose C2. That means both the glucose and fructose, the anomeric carbon is linked to form the glycosidic bond. That's why no free anomeric carbon is present for the reducing nature. That's why combinedly the sucrose is non-reducing disaccharide. Next, some common disaccharide and their structure. First one, the sucrose, which is also known as the cane sugar. It is composed of the glucose and fructose. The alpha D glucopyranose is linked with the beta D fructofuranose, and that alpha 1 is linked with the beta D of fructose. So the linkage is the alpha 1 beta 2 between the C1 of alpha glucose and C2 to beta fructose. This is the Haworth conformation and this is the Fischer projection. We can see easily the C1 of the glucose is linked with the C2 of the beta fructose unit. What are the properties? That C1 of glucose and C2 of fructose, both the anomeric carbon are attached for the glycosidic bond. That's why there is no free anomeric carbon. That's why sugar is non-reducing in nature. It is commonly found in the table sugar. It is an important source of dietary carbohydrate. It is sweeter than most other common sugars except the fructose. Sucrose is employed as a sweetening agent in food industry also. The intestinal enzyme like sucrase hydrolyze the sucrose and form the glucose and fructose. The next important disaccharide is the lactose, which is also known as the milk sugar. We can found it in milk. It is composed of glucose and galactose. The beta D galactopyranose is linked with the alpha D glucopyranose. The beta 1,4 glycosidic linkage is there. That means that the C1 of beta D galactopyranose is linked with the C4 of the alpha D glucopyranose. That the C1 of beta D galactose is linked with the C4 of the alpha D glucopyranose. So the bond is beta 1,4 glycosidic bond. So here the glucose C1 is free. So glucose is reducing but galactose is non-reducing. So the combinedly the lactose is reducing in nature. Hydrolysis of lactose by emulsin indicates that its non-reducing galactose is present in the form of beta-galactoside. C1 of non-reducing galactose is linked with the C4 of reducing glucose. It is reducing in nature and present in milk and other dairy product. Next, the maltose. It is composed of two glucose units linked by alpha 1,4 glycosidic linkage. That means one alpha D glucose unit held together by alpha 1,4 glycosidic linkage. That means one alpha glucose C1 is linked with the another alpha D glucose C4 molecule. So one alpha glucose is reducing in nature because they have the free anomeric carbon, but other alpha glucose whose C1 is actually attached, this alpha glucose is non-reducing in nature. So in the picture we can clearly see that this alpha glucose C1 is actually participating. So this is actually non-reducing in nature. But other alpha glucose, this one, C1 is free. Here C4 is linked. So this alpha glucose actually is reducing in nature. So the combinedly it is the reducing sugar as a whole and formed during the digestion of starch. Cellobiose is the another disaccharide and it has an identical structure with the maltose except that the form has a beta 1,4 glycosidic linkage. In the case of maltose, both are alpha D glucose, but in the case of cellobiose, both are beta D glucose. The linkage is same. For the maltose also here alpha 1,4. In the case of cellobiose, it is beta 1,4 glycosidic linkage. Cellobiose is formed during the hydrolysis of the cellulose. Other than these common disaccharide, there is some synthetic disaccharide also like lactulose. Lactulose it is a synthetic disaccharide similar property like lactose. It consists of one molecule of galactose and one molecule of fructose. Normally the lactose is formed one molecule of galactose and one molecule of glucose. But in the case of lactulose, that one molecule of galactose and one molecule of fructose. It is present in the produced by industrially normally by the isomerization of the lactose via 1,2-enediol intermediate. During heating to more than 70 degrees centigrade in alkaline solution, lactose isomerized to an equilibrium mixture of 20 to 30% lactulose and 70 to 80% lactose. Other than the lactulose, another synthetic disaccharide is there which is known as sucralose. It is known as a artificial sweetener. It consists of 4-chloro-4-deoxy alpha D-galactopyranose and 1,6-dichloro-1,6-dideoxy beta D-fructofuranose unit. Both are linked by a glycosidic bond. It has a role as an environment contaminant. It has a xenobiotic nature also. Sucralose is actually 500 times sweeter than sucrose, but it is not digested. Hence, no calories are supplied. It is acceptable in terms of taste, safety and stability. And it is also safe for the consumption by the diabetic and non-diabetic patient. One important property for the disaccharide is the inversion of sugar. Inversion actually refers to the process in which a disaccharide, most commonly the sucrose, is hydrolyzed into its component monosaccharides. For sucrose, the inversion produces the glucose and fructose, and collectively the sucrose is known as invert sugar. What is the mechanism? The process is hydrolysis reaction when water is used to break the glycosidic bond in sucrose. The sucrose has a alpha 1 beta 2 glycosidic bond because the alpha glucose C1 of alpha glucose is linked with the C2 of beta fructose. So after the hydrolysis, the glucose and fructose will form. The hydrolysis can be catalyzed by acid or any enzyme like invertase. So sucrose, with the help of this enzyme and by the water molecule, it will form the glucose and fructose molecule. There is a change in the optical activity. That's why it is known as the inversion. Sucrose, normally it is a non-reducing sugar with a specific optical rotation, that is plus 66.5 degrees. So it has a dextrorotatory in structure. When the sucrose is hydrolyzed, the optical rotation actually changes. So it is converted from dextrorotatory to levorotatory. It is known as the inversion of optical rotation. So from plus 66.5 degree to, it is converted to minus 28.2 degree. The process from dextrorotatory to levorotatory conversion is known as inversion. And the hydrolyzed mixture of sucrose that contain the glucose and fructose is known commonly as the invert sugar. Hydrolysis of the sucrose by the enzyme sucrase or dilute acid liberate one molecule of glucose and fructose. It is postulated that sucrose, it is in dextrorotatory structure that is have a plus 66.5 degree optical rotation, is first split into alpha D glucopyranose and beta D fructofuranose. Both are dextrorotatory in nature. Alpha D glucopyranose is plus 52.5 degree. But beta D fructofuranose is not stable. That's why immediately it is gets converted to beta D fructopyranose structure, which has a strong levorotatory nature, and the optical rotation is minus 92 degree. That's why overall effect is that dextrosucrose plus 66.5 degree on inversion is converted to the levorotatory, that is minus 28.2 degree. So that's why this total phenomena is known as a inversion of sugar. In the reaction also it is clearly say that sucrose, it is the dextrorotatory structure, has an optical rotation of plus 66.5 degree. With the help of any enzyme or any acid, it is converted to the glucose and fructose. That glucose, that is the alpha D glucopyranose, that has a dextrorotatory nature, optical rotation plus 52.5 degree, and fructose, that is the beta D fructopyranose, has a levorotatory in nature minus 92 degree. So combinedly, the overall effect, it is the levorotatory and has a optical rotation minus 28.2 degree. So the total phenomena is known as the inversion of sugar. So lastly, what is the key highlights of this today lecture? That's the overview of the carbohydrate, that it is a polyhydroxyaldehyde or ketone, has a general formula of CH2O whole N. It serves as an energy source and structural components. It can be classified as a monosaccharide, disaccharide, oligosaccharide and polysaccharide. The structure of the monosaccharide we can represent in three forms. One is the Fischer projection, the 2D representation of the open chain form. The vertical line, the top position is the oxidized group. Horizontal bonds project out and vertical bonds project behind. It has two configurations depending on the orientation of the hydroxyl group at the penultimate carbon. If OH in the right hand, it is D form. If OH in the left hand, it is L form. According to the optical activity, it can also has a dextrorotatory and levorotatory property, but it is not linked directly with the capital D or capital L nomenclature. That it has also the cyclic representation like the Haworth and chair conformation. Haworth is also the 2D structure of the cyclic form. It is actually visualizes the alpha and beta anomer. If C1 carbon OH downward, then it is alpha, and if C1 carbon OH is upward, then it is beta. If it is 6-membered ring, it is known as pyranose. If it is 5-membered ring, it is known as furanose. Chair conformation is the 3D structure of 6-membered ring, highlights the axial and equatorial position. And when the bulky groups in the equatorial position, then this structure is mostly stable. And chair flip actually converts the axial to equatorial without alternating any configuration, D or L, alpha or beta, anyone. Then the disaccharide formed by the condensation reaction between the two monosaccharides unit, formation of a glycosidic bond with the release of the water molecule. Glycoside bonds actually form that one carbohydrate anomeric carbon is react with the another carbohydrate or non-carbohydrate hydroxyl group. It is, if it is linked with the carbohydrate to carbohydrate, it is known as glycoside. If carbohydrate to non-carbohydrate, then it is known as glycon. Then based on the reducing ability, disaccharide we can also divide as a reducing disaccharide and non-reducing disaccharide. If has a free anomeric group, then it is reducing. If there is no free anomeric group, then it is not possible for the reducing nature. That most common example of the disaccharide is the sucrose, lactose and maltose. Apart from this, there are some synthetic disaccharide also, that is the lactulose and the sucralose. Sucralose act as an artificial sweetener. And the most important property for the disaccharide is the inversion of the sugar. That means the changing the optical rotation from dextro to levo or vice versa is known as the inversion of sugar. In the case of the sucrose is actually dextrorotatory normally, but after the hydrolysis, the sucrose is converted to the levorotatory in nature, and after the hydrolysis, it will form the glucose and fructose. Combinedly, it is known as a invert sugar. That's all for today. Thank you. Next day, we will describe about the detail of polysaccharide and other properties of the carbohydrate. Thank you.